Every number an engineer uses is associated with some physical parameter called a dimension. For example, does the number correspond to the length of a rod, the pressure in a tank, or something else? In addition to the dimension, we need to know the units used to represent the dimension. Is the rod length in meters, feet, or inches? If we don't know the dimension and the units involved, the number itself is meaningless. This video introduces dimensions, units, and dimensional analysis, which is simply the rules of mathematics as applied to dimensions rather than numbers. Parameters that describe a physical system are called dimensions. Examples of dimensions are things like length or distance, time, temperature, mass, force, and charge. Let's think in terms of this block of material. The length, width, and height of the block are all lengths or distances. However, there are more than just these dimensions. If I apply heat to the block, its temperature will change. Temperature is a thermodynamic dimension rather than a geometrical one. If I'm concerned with the temperature of the block as a function of time as it heats up, time becomes another dimension of the system. If we apply a force to the block, it'll start to move. The mass affects the rate at which the speed increases, so under those conditions, the mass and the applied force both become dimensions. So keep in mind that the dimensions associated with a physical system are related to what is important about the system for the problem at hand. Dimensions are not necessarily just the geometric size of the object. In order to be useful to engineers, dimensions have to have numerical values. As one of my professors used to say, an engineer's job is to make a number. Numerical values associated with dimensions are relative to a system of units. Without knowing the units, the numerical value itself is meaningless. Length, for example, can be measured in feet, inches, meters, or a variety of other units. We can say that a rod is 3 feet long, 36 inches long, or 1 yard long, all of which are equivalent descriptions of the rod's length. Conversely, a 12 centimeter long rod is nowhere near the length of a 12 meter long rod. If you don't know the units of length, the actual number associated with the length is useless for performing engineering calculations. Time is usually expressed in seconds, though minutes, hours, and weeks are also possibilities. Temperature can be degrees centigrade, degrees Fahrenheit, or degrees Kelvin. Mass is measured in kilograms, though slugs are used as English units. Force is measured in newtons or pounds. Sometimes pounds of force are abbreviated lbf for pounds force. All of these units have abbreviations which should be included with any number so that everyone knows how to interpret the number. Abbreviations are given in parentheses after the name of the unit here. Sometimes units are defined in terms of combinations of other units. This allows us to more easily represent the units of some common parameters that aren't fundamentally dimensions themselves. For example, the fundamental dimension of electricity is charge, whose units are coulombs. However, for many calculations, charge itself is an inconvenient parameter to work with. Current can be a more directly useful parameter. It's the rate at which charge passes a point. Therefore, its units are coulombs per second. Since current is such a commonly used parameter, this is defined as another unit, amperes, abbreviated as a capital A. Energy or work is another parameter engineers work with a lot. Work is force times the distance traveled. If units of force are newtons and units of distance are meters, work is newtons times meters. This is usually redefined as joules, abbreviated as a capital J. The final example is pressure. Pressure is a total force divided by the area over which the force is applied. In the metric system, area is the product of two lengths, measured in meters, and force is measured in newtons. The ratio of newtons to meters squared is called pascals, abbreviated as a capital P followed by a lowercase a. Defining the dimensions and their units allows you to do dimensional analysis. This simply consists of performing math with units. We already did a little of this on the previous slide when we defined a new set of units based on ratios or products of other units. This is an extremely powerful tool, but it's fairly easy to use. You just apply mathematical operations to the units associated with a number exactly as you do to the numbers themselves. For example, velocity is defined as the rate of change of position with time, so it's just the ratio of the distance traveled to the associated time. I can multiply both sides of this equation by time. The times in this expression cancel out, so velocity times time is equal to distance. So if the velocity is 50 meters per second and the time is 10 seconds, the time cancels out of these two expressions, leaving the result to be 500 meters. Dimensional analysis can keep you from making silly mistakes. Always show your units when making a calculation and include the dimensional analysis in your calculation. If the dimensions of your result don't match the dimensions you should get, you're almost surely doing the math wrong. Units are often preceded by prefixes. This makes it simpler to represent numbers that may span ranges of several orders of magnitude. To keep from having to write a lot of zeros to represent a number, we define prefixes that specify multiplicative factors of 1,000. This table shows common prefixes. The first column is the multiplicative factor, the second is the name of the factor, and the third is the abbreviation that's used in the unit name. Here are a couple of examples. 1 kilometer, K, is 1 times 10 to the third meters, or 1,000 meters. 1.5 milliamps is 1.5 times 10 to the minus third amps, or 0.0015 amps. Finally, I'll talk about unit conversions. Sometimes the way a number is measured isn't consistent with the formula you want to use the number in. For example, suppose you have a velocity in kilometers per hour and you want to find the number of kilometers traveled in 20 seconds. Distance is velocity times time, as we saw before, but only if the units of time are consistent. In this case, you'll need to convert the time period to hours or express the velocity as kilometers per second. So let's take a look at this example in which we know that a car travels 10 kilometers in 20 minutes. We want to find the car's velocity in units of meters per second. Probably the easiest approach is to individually convert the distance and the time to the desired units before calculating the velocity. 1,000 meters is equal to 1 kilometer, so 10 kilometers is equal to 10,000 meters. There are 60 seconds in 1 minute, so 20 minutes is 1,200 seconds. Velocity is the distance traveled divided by the time. So in our desired units, that's 10,000 meters divided by 1,200 seconds, which is about 8.3 meters per second. There are lots of different ways to do this problem. An alternate approach would be to calculate the velocity in kilometers per minute. That calculation gives a velocity of 10 kilometers over 20 minutes, or 0.5 kilometers per minute. Then we can convert kilometers per minute to meters per second. Since 1,000 meters is 1 kilometer, there are 1,000 meters per kilometer. Likewise, there are 60 seconds per minute. The velocity is in kilometers per minute. So doing my dimensional analysis, I have kilometers per minute. Now if I multiply that by meters per kilometer, the kilometers cancel and I get meters per minute. Now, if I have units of meter per minute and divide that by seconds per minute, which results in a unit of minutes per second, since I invert this if it's in the denominator, now the minutes cancel and I get meters per second, my desired units. So my final calculation is going to be 0.5 kilometers per minute times 1,000 meters per kilometer divided by 60 seconds per minute, which again ends up to be about 8.3 meters per second. Notice that when I was doing this problem, I didn't really worry too much about the actual approach, but no matter what I did, I kept track of the units on the individual terms and made sure that the dimensional analysis turned out correctly. If the dimensional analysis works, I can be pretty sure that the numerical values I'm multiplying and dividing by are correct. Mathematicians' numbers can be abstract, but engineers' numbers need to include units in order to give the numbers meaning. Indicating units and following dimensional analysis can also save you from some silly errors. If the units don't work out, the calculation itself is probably wrong.